Sasika students, let's go for lecture number 2, Thermodynamics class 11. Students, what is state of a system? For thermodynamics, a thermodynamic state of a system is its condition at a specific time. This is fully identified by values of suitable set of parameters known as state variables. You can call them state parameters or you can call them thermodynamic variables. Once again, the state of a system is basically condition at a particular time. Why I say time? Because as the time changes, maybe with the change of time, the state variables may change. And if the state variables change, the state of the system will also change. Right? So, state of a system depends upon its state variables. What are the state variables? Let us see. Students, state variables, what are state variables? A thermodynamic state is specified by 5 state variables, right? What are the 5 state variables? Number 1, pressure. Let us talk about, students, that this is a container, right? Now, in this container, let's say we have some gas in this, right? Now, obviously, the gas will have some volume equal to the volume of this container. It will have some pressure. It will have some temperature, right? So, let's say at time, let's say 10 o'clock, 10 a.m. Let's say I can say the state of the system is represented by 1. So the state is, see it's written here, state is the condition at a specific time. Let's say at 10 o'clock, that is fully identified by values of suitable set of parameters. What are these parameters? These parameters are state variables. Some values of these parameters, I will tell you what is meaning of this. At 10 o'clock, students, choose, suppose we put a Bourdon gauge in this. Now, Bourdon gauge has a spring inside this. When these molecules of the gas will, exert some force on the spring, it will give the reading of the pressure in Pascal or whatever units. So, we will note down the pressure and internal volume of this container is the volume of the gas, and we can measure the temperature. Let's say we are having a thermometer, you know so with this thermometer we are able to measure the temperature. So 3 state variables are defined: volume, pressure and temperature. So these 3 state variables we observe for some time, they are constant. So we can say it's in equilibrium. We can say the state is, let's say, represented by 1. This is the state of system. Now students, I want to change the state of the system. How will I change the state of this thermodynamic system? Let's say I put some burner or some lamp, burning thing below this. So what will happen? The molecular interaction of the molecules or atoms, whatever it is, will increase. Collisions will increase. As a result, the temperature will rise. Now it may become T dash. Now after 5 minutes, let's say at time 10:05 a.m., I again measure temperature. Now temperature will be, different. Maybe the pressure will also change. Obviously, pressure will increase. So this reading will show more pressure. Well, the volume is same. Volume cannot change. So now this is state number 2, which is represented by new value of pressure, P dash, new value of temperature, T dash, and third state variable, V is constant. V is constant. V cannot change as long as this lid is fixed. It's a constant volume. Okay. So this is the example how the state variables are changing to give new state of the system. This is the understanding of state and state variables. All right, students. Now let's go further. Okay. Now, I also want to mention here, students, that at a particular time, at a particular time, it's very important that you can measure pressure, you can measure temperature, you can measure volume, you can measure other thermodynamic variables like internal energy and entropy also. Entropy, degree of randomness. We will discuss and study entropy in detail possibly. Let's see whether your syllabus allows. And internal energy in this lecture only. Okay. So at any time it is possible to measure the values of every of the state variable. Okay, it's very important. Remember that. Okay. Now, other thing, let's go further. Let's talk about heat, internal energy, and work. Okay. So, students, internal energy, when we talk, the simple definition of internal energy is the sum of kinetic energy and potential energy of the molecules. Which molecules, students? Let's see. We have taken this as a system. Yesterday we have defined a system. Any space or anything, you know, with well-defined boundaries or even imaginary boundaries where our attention is focused, pertaining to thermodynamics is known as system. Yesterday we have studied system is separated from surroundings by the boundary. Boundary can be imaginary, it can be real boundary also. For example, let's talk about isolated system universe. Universe boundary is not fixed. It has imaginary boundary. So this system, suppose I have taken, let's say again it's a system of some gas. Now it has some molecules, some finite molecules. Okay. Now guys, these are the molecules. Now uh, all the molecules will have the potential energy and they will have kinetic energy also. But yesterday we have studied thermodynamics study do not go to the microscopic level. It explains everything on the macroscopic level. But we know that every molecule or every atom in this gas has some kinetic energy and some potential energy. Now, as such, this container which is containing the gas is not moving. It's not moving. Okay, so we can say the kinetic energy, net kinetic energy of this system. As such, macroscopically, this container is not moving, so it appeals to us that kinetic energy is zero, right? But the individual molecules have three kinds of motion. They can have transitional motion, they can have a rotational motion, they can have vibrational motion. Also, owing to these three motions, there is kinetic energy. These molecules are having. So sum of all these kinetic energies and sum of the individual potential energies of these molecules is the internal energy of the system. You might wonder, are we going to enter the gas, measure individual kinetic energy of every system, then measure kinetic energies of all the system, and then potential energy of all the points, and then find the internal energy of the whole system? No, not. It's so simple. Okay. So we use notation which is a macroscopic variable. It's a macroscopic variable, though its concept originates from the microscopic behavior of molecules, but it's a macroscopic variable. We can measure it. We need not enter and understand the individual kinetic energies of the molecules. Okay, kinetic energy. Okay, now internal energy is done. It's the simply sum of all the kinetic energies and potential energies of this molecule. How we measure it? Let's see. In the coming time. All right. Now, internal energy is a function of temperature. We want to measure the internal energy. We get an idea about you know what is the internal energy of a system by knowing its absolute temperature. All right. So you could say that, it's so difficult to imagine a body at absolute temperature, that is 0 Kelvin, right? Our 0 degree centigrade is equal to 273 Kelvin, remember that. And 0 Kelvin is basically minus 273 degrees centigrade. Uh, not so easy to achieve this temperature. And I really wonder if we have really achieved this temperature so far or not. There are cryogenic temperatures, very, very less, like minus 70, minus 80 degree centigrade, but this temperature not being achieved till now. Now, every substance above this temperature, above 0 Kelvin, has kinetic energy. It's a function of temperature. Now, internal energy of a system of a mass of gas depends upon state described by specific volumes of pressure, volume of temperature. It does not depend upon how the state of the gas came about. Pressure, volume, temperature, and internal energy are thermodynamic state variables of system. Okay, that's fine. I have read this from your NCERT text, and I thought students might have little tough time understanding what is told by this. I read it once again. Internal energy internal energy of a system of a given mass of gas, means some system, depends upon state, depend upon its state. A state is always described by specific volumes of pressure, volume, temperature. These are all state variables as we have discussed above. Just see this. See, we've already discussed that state of the system is basically the condition of a system at a specific time, which is fully identified, or which is fully characterized, or which is fully defined by values of state variables, maybe two state variables, three, four, five. Okay, any of the five state variables we can take. What are the state variables? Pressure, volume, temperature, internal energy, and entropy. And I also told you it is possible to measure the value of this pressure, these state variables, at a given point of time. This is very, very important. I'll explain you in this lecture only what is the meaning of this. Okay. There are certain things which we understand the meaning as per mechanics and as per physics and other chapters do not have the relevant meaning in thermodynamics. It's a different science. It's a different part of physics which has different notations and different way to understand. So once you listen to the complete lecture, you are going to get little bit of it. You listen to it again, you're going to get more of it. I will also tell you, students, that it was once mentioned by world famous two or three authors of the who have written great books on thermodynamics, that once you read the book, or twice or thrice you read the book, you may understand a little bit of it. So repetitiveness and consistency is important in this subject. Now, what is the meaning of this? That internal energy of a system depends upon state described by specific volumes of pressure, volume, and temperature. It doesn't depend upon how this state of the gas came about. What is the meaning of this? It does not, it means this internal energy does not depend upon how this state of the gas came about. That means internal energy at a particular time can be measured. It doesn't matter how the state was changed, means whether we used a burner with low flame, whether we used a burner with high flame, or with a medium flame to change its states from 1 to 2. Internal energy doesn't depend upon that. But are there things which depend upon the path? In order to understand this, I'm going to give you an example of a piston cylinder. Students, this is your piston, and this is your cylinder. This is your cylinder. We have piston cylinder in every automobile, which is responsible for all your motions across the world, right? Now let's say this piston is on the top, described by state 1, and we have just now understood the state is always described by fixed values of some state variables. In this case we have taken three state variables: pressure, volume and temperature. How we are going to measure the pressure? I've already told you, we can insert a Bourdon gauge in this which can give us the value of pressure. Then volume, already obviously we can measure the volume also, and we can measure the temperature also. Physically we can measure these three things, okay, macroscopically, okay, without wondering what is the pressure and temperature of individual particle. Without wondering, macroscopically we can measure this. That's why these are known as macroscopic variables also. Okay students, now what we do, we apply some force here. Okay, we applied some force on the top of this piston. This is piston, this is head of piston, this one, this portion is head of the piston, this is piston. Now piston moves down. When the piston moves down, students, what will happen? The volume will decrease. Initial volume is V. The final volume may become, let's say this is V, and the final volume is V dash. And when you compress the gas, its molecular collisions increase, temperature increases, its temperature, let's say, become T dash. Pressure will also increase, it becomes P dash. These new state variables or thermodynamic variables, I have given three names to state variables. Different books you study, there will be different names of the state variables. These are known as state variables, state parameters, or thermodynamic variables. Whatever it is, they are same: pressure, volume, temperature, internal energy, and entropy. These five, any of these five. Okay students, let's go further. So I pressed the piston down. Piston moved from, the system was in state 1, and when the piston reached here, the system is in state 2. Now what is the volume? This is the volume of my system. This is the volume of my new system. New system. All right. So my system has, the volume has decreased, the pressure has increased, the volume has decreased, the temperature has also increased. Okay. Now at different points, you know, at intermediate states also, let's say I have been able to record the values of pressure, volume and temperature, and I use two state variables, pressure and volume, to plot this graph. See, this arrow of the graph in thermodynamics is important, showing that the system has gone from state 1 to state 2, right? At state 1, what were the state parameters? P1, V1. At state 2, what were the parameters? P2, V2. Right? I wrote here P dash, V dash. Please make it P2, P2, V2. Okay. Now students, this is the path. This is the curve which is showing how the system has attained state 2 starting from state 1, and so many infinite intermediate states also system must have encompassed. All right. Now students, what is the work done? Work done. Let us see. We want to calculate the work done, especially thermodynamic work done. Okay, concept is same. In physics, if you remember, work done is equal to force into distance. Do you remember? Here also basic concept is same, but we define in some other way. I'll tell you how. Work done in thermodynamics is equal to PdV. Okay, when I say PdV is pressure into change in volume, because we believe when there is a pressure on this, okay, when there is a pressure on this, so the volume will definitely change. Like the change in volume in this case is basically V2 minus V1, right? So this, or P dash minus V, PdV. Now pressure into dV is again having the units of work done. Also how? If you just see, pressure is Newton per meter square. and volume is meter cube. So this is equal to again Newton into distance. I'm sorry, no, Newton into meter, that is equal to Newton into meter is joule. PDV work. Thermodynamic work is known as PDV work. It is done because of some pressure on the piston and as a result of some change in the volume. If there is no change in volume, if dV is 0, if there is no change in the volume, we say the pressure. We can write pressure as del W. There's a reason why we write del, not dV. dW is equal to 0 because the force, the pressure are not able to do any displacement in the piston. Okay, work done is PDV. Students, work done can be calculated from this graph also by calculating the area under this curve. Okay, if you remember your ninth lectures, your teacher must have told you, students, when he was talking about, velocity time curves or displacement time curves. If you remember, especially the velocity time curve. Suppose this is your velocity time curve. Let's say some certain thing is going with constant acceleration. So this straight line is your velocity time curve. Now, if you remember the area under this, well, this is velocity, this is time, ninth class. The area under this curve, if you remember, your teacher must have told you product of these two variables is what? V into T is actually displacement. So area under this curve will give you the displacement, net displacement from point 1 to point 2. Let's forget about this. I just told you to, so that you remember, what was told to you in 9. So, and then whole, if we can say, if on y-axis, if we have a variable, and on x-axis, if we have a variable, if the product, whatever is the product of the variable, that area under the graph will always be equal to product of this variable. Area is length into breadth. That way also you can understand this. Here, we know thermodynamic work is PDV, and this is pressure, and this is V2 minus V1 is dV, change in volume. So students, if you want to find out the work done when the system moved from this point to this point, then this will be your dV, and P into dV, some average value of pressure. You might wonder how we will calculate B. So there are ways to calculate mean pressure, though the pressure is not constant. Find out the mean pressure. That mean pressure multiplied by dV is thermodynamic work done from this point to this point. Okay, but in this case, we want to take the work done from 1 to 2. So this entire area is the work done by the piston. Work done by the piston. Work done by the piston, as it moved from state, as the system moved from state 1 to state 2. Now students, tell me one thing. We started with this, hope you have not forgotten, that there was a statement that the internal energy depends upon initial, can be measured at a point. It doesn't measure, it doesn't depend upon how the state of the gas, state of the system was changed. Students, in this particular case, the system has gone in this path from 1 to 2, right? Imagine if the system takes a different path, 1 to 2, what will be the work done? You will agree with me that this much area will be added, and area under the curve is the work done, so work done would have increased by this much amount. That means the work done from 1 to 2 does not really depend upon initial and final states. What are the initial states? What are the initial thermodynamic state? Initial thermodynamic state is represented by 1, and that depends upon the values of pressure, volume, and temperature P1, V1. 2 state is represented by P2, V2, fixed values of thermodynamic variables. This work done is not only dependent on the values of thermodynamic variables at initial and final position. It also depends upon the path taken. Suppose the path taken was like this. Suppose, let's say, somehow the pressure increased like this and then like this, then the work done would have further increased by this. Okay, but now you have understood that this work done depends upon the path taken. Similarly, some other day I'll prove students the heat transfer. This also depends upon the path incurred, not simply, the initial and final variables. Okay, now I'll give you another example, students. Give me a second. Okay, now let's say you ask some student to run from this point to this point. This is point A and this is point B, and the shortest distance between A and B is, let us say, 10 meters. Okay, now let me take you 2 minutes away from thermodynamics. Students, I ask the student to run in the first case and reach here. Obviously, he will take less time. In the second case, I will ask the students to just walk leisurely and reach this point. Okay, he will take more time. I simply ask the students to, walk very far, very slowly, like a old man with a stick, and take maybe half an hour to reach here. Okay, in all the three cases, is the distance traveled same or different? In case this person is walking on the straight line, any student can answer me. A student has come from A to B by running, by walking, or by very slow walk, but he has not come like this. He has come along a straight line. Is the distance traveled in all the three cases, Ishma, is same or not?
Sir, it is same.
It is same. That means the distance traveled here, suppose S, actually S is not a thermodynamic variable. And I'm giving you example, taking you out of thermodynamics. If S had been a thermodynamic variable, now S depends upon what? Initial and final only. Let's say I start measuring distance from this point. So here the distance is, let's say, 25 meter. Here the distance from the origin is 35 meter. So what will be the distance? I will simply say 35 meter minus 25 meter is equal to 10 meter. Here, students, the distance traveled is not a function of path. Though in the first case, person ran and covered the distance. In the second case, person simply walked and covered the distance. But it did not affect the distance traveled. But students, you see, now I'm talking about heat transfer. See if it depends upon path or not. I'm giving you example. You may relate it to thermodynamics. Somebody might say it is not related to thermodynamics. Doesn't matter. Just giving you the root understanding of heat transfer. Suppose there's a person, you ask him to lift the dumbbells. These are the dumbbells. You give some dumbbells to him, 2 kg dumbbells, 1 kg, depending upon his capacity, and you ask him to, work on, take both the dumbbells in both the hands, and simply, put them up and down. Now, in the first case, you asked him to put the dumbbell up and down slowly for, let's say, 2 minutes. Right? Now, do you feel that after he has done the work with the dumbbell, the temperature of the body would have changed? Do you think so? Let's say it's winter, the person is simply standing. You ask him to simply, put these dumbbells up and down for 2 minutes. Do you think he will sweat and his body will become hot? His temperature will increase? Do you think so? After doing some work in the winter, do our temperature of the body increase or decrease? Come on, students. In winter season, when we do some work, do we sweat or not? We sweat, our temperature increases. In the second case, you ask him to do the work done, means dumbbell very fast. Very fast means, up, down, up, down. The frequency should be more. But the time limit is again same 2 minutes. So the amount of heat transfer from his body would be more in the second case. Third, you simply ask him to increase again more frequency. Very fast put the dumbbells up and down. The heat transfer as well as the work done by the person in all the three cases, tell me students, will be same or different? It will be different, right? Especially heat transfer would be different, right? Or you can also say the person's, if he's slowly putting dumbbells up and down, he will say, I have not done so much work. But if he is doing the work at a very fast rate, he will say, I've done more work, right? Now, this is the understanding that heat transfer and work done in thermodynamics, these are you know these are not state variables, but we call them state functions, or some books they call them path variables. One is state variable. State variables value can be measured at any time, only at any time. But path variable, if you want to measure their value, you cannot measure the value of path variable at any time. Something exactly what we did when we started limits and derivatives, students, if you remember. And it was not possible for us to find out the average velocity of the ball, which was you know coming down at some particular time. Let's say when the ball is moving down with the displacement of 4.9 t square, if I say what is the velocity of the ball at 4 seconds, we cannot find out, because at 4 seconds delta t is 0. So I cannot find out the average velocity, because to calculate average velocity, I need distance traveled, delta s divided by delta t. Since delta t was 0, I'm not able to calculate the instantaneous velocity at 4 seconds. Calculus helped me. Limits and derivative helped me. Same concept here. If you want to, if this is a cylinder, right? This is a piston. No matter, from this volume, let's say from this volume, this is piston. Let's say I ask the piston to be brought to half the volume. You can bring it slowly, you can bring it fast, you can bring it very fast. But whether you, it doesn't matter how you bring the piston from this position to this position, the change in volume is same or different. Any student? Let's say when the piston is here, it's full volume. When the piston is here, it's half volume. I ask the student to bring this piston very fast here, then slow, then very slow. Irrespective of this, finally the change in volume is half the volume. That means delta V, or volume, is not path variable. It is state variable. State variables, you can find out their values at a given time. You need not have an interval to calculate their values. A very important aspect. With this, I finish this lecture for today. If you possibly see the video again, every word spoken, you might understand better, along with reading of a book. I wish you all the best. Have a nice time.